Hey everyone, you knew it was coming. The last lesson was dealing with the product rule. Today we're going to talk about the quotient rule. Those just go together. It makes sense. Once you've talked about multiplication, you're going to start talking about division. Now, one thing I'm going to promise you here, this is probably going to be the quickest lesson of the year because it's just a practice of learning the quotient rule and then practicing it. So quotient rule is the idea of being able to take the derivative of a quotient or a division of two separate functions. Okay, and that's our goal today. So here's what the quotient rule says, and in some funky context, it says that if u and v are differentiable functions, then the derivative in respect to x of u divided by v is equal to the derivative of u in respect to x times v minus the derivative of v in respect to x times u all over v squared. Now that is really wonky, right? It's like weird to look at, weird to read. I get it. Let me rewrite it in a different way. If I have f of x and that is equal to, let's say, g of x over k of x, then the derivative of f of x, f prime, is equal to the derivative of the top thing, so it would be g prime of x, times the bottom thing, times x, minus the derivative of the bottom thing, so it'd be k prime of x, times the top thing, so times g of x, and then all over the bottom squared, all over the denominator squared. So this actually does resemble the product rule in that, let me go ahead and write that down, right, so we can see a comparison. Let's say I've got f of x equals g of x times k of x. Well, then the derivative of that would be g prime of x times k of x plus the derivative of k of x times g of x. So you can see the similarities. Obviously, there's going to be some differences here, but the similarity is obvious. The first thing is the same. The second thing is the same. The first term and the second terms are the same. Notice this, in the product rule, you could actually mix this up and still be okay because addition is commutative. You could say k prime times g plus g prime times k, and if I flip those, it's okay. It's not going to affect it because it's commutative. But with the quotient rule, you can't mix it up because we have subtraction. So if you mix it up, you're going to get an opposite sign, and we don't want that. And so the way I think about it is putting it into words. The derivative of the first times the second plus or minus the derivative of the second times the first. In this case, obviously the first thing is the first thing. So the derivative of the first times the second plus the derivative of the second times the first. In this case, the first thing that we read is just like we would read a book. It's the top thing. The derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. So there it is in words. There it is in words. There it is in English. The derivative of a quotient is equivalent to the derivative of the top times the bottom minus the derivative of the bottom times the top, right? All over the bottom squared. Okay? That's that. Now you can see that this is a little bit cleaner to write it like this. If u and v are functions, then it's u prime v minus v prime u all over v squared. Okay? So that is the quotient rule. Pretty straightforward. Let's go ahead and take a look at an example of what that looks like. And so in our example, we have, I'm actually going to give a different example to start off. We'll do that one in a second. If I say y equals 3x to the third over x to the fifth, okay? Now again, there's a quick way, short way of doing this. I could just rewrite this as y equals 3x to the negative second, and then take the derivative from there. So y prime equals negative 6, x to the negative third, and if I want no negative exponents, I put negative 6 over x cubed. So that's fine. That would work fine. If I apply the quotient rule, we would say the derivative of the quotient is the derivative of the top thing, so 9x squared, times the bottom thing, minus the derivative of the bottom thing, so 5x to the fourth, times the top thing, so 3x cubed, all over the bottom, so 5, or x to the fifth, squared. And then simplifying that, we end up with 9x to the 7th minus 15x to the 7th, all over x to the 10th. Because those have the same exponents, I can put them together. I end up with negative 6x to the 7th over x to the 10th. And then we subtract those exponents, we end up with negative 6 over x to the 3rd. Same result. Just kind of verifying it works a little bit. Again, I'm not proving this in the video today. If you would like to see the proof, you can watch the video on the proof for the quotient rule. But looking at our example here, we got y equals x squared over 2x minus 5. Now maybe we can rewrite this somehow in a different form that would allow us to use a different rule. But it's simple enough to see it's a quotient, right? It's a division of two functions. So the derivative is going to be 2x, the derivative of the top thing, times the bottom thing, so times 2x minus 5, minus the derivative of the bottom thing, so the derivative of the bottom thing is just 2, because the derivative of 5 is 0, and then times the top thing, so times x squared, all over the denominator squared, so all over 2x minus 5 squared. Now we can simplify this a little bit by distributing. We end up with 4x squared minus 10x, and then minus 2x squared, all over, we could expand this to be 4x squared minus, what is that, 20x plus 25, if we would like. And then simplifying it further, we can combine like terms on top. 2x squared minus 10x, all over 4x squared minus 20x plus 25. Now, with that said, again, we don't have to go through and simplify everything down to this form. You can see in my lesson that it's not the same exact form. I left it in factored form in the bottom. And in fact, I would argue that leaving it in the factored form in the bottom is going to actually make things simpler when you're going on to maybe find the slope of a tangent line at a given point or something along that line. So there's my example of the quotient rule. All right, like I said, this is going to be a short lesson. Just a few practice problems for you to give a try. So go ahead and pause the video, see what you come up with on these. I will tell you that number 5 is going to take a little bit more time than the rest of them. All right, for number 1, we have y equals 4x cubed minus 3x squared all over 4x to the 5th minus 4. And we're looking for the derivative of that, obviously. We see that we have a quotient here, so it's going to be y prime equals the derivative of the top, so 12x squared minus 6x, put those in parentheses, times the bottom, so times 4x to the 5th minus 4, minus the derivative of the bottom, which is 20x to the 4th, and that's it, times the top, so times 4x cubed minus 3x squared, all over 4x to the 5th minus 4 squared. So that is my derivative. I could simplify that further. I don't really want to, though, because it's just algebra from there. So let's not do that, okay? If you distributed everything out and spent all that time working, good for you. Number 2, we've got f of x equals 5 over 4x cubed plus 4. 4x cubed plus 4. Now, I'm actually going to do this two different ways. We see that we have a quotient here, so we can apply the quotient rule, obviously. But here's kind of the interesting thing about this guy. Because the top is a constant, what is the derivative of the top? Well, the derivative of the top would be 0. And then times the bottom, so times 4x cubed plus 4, minus the derivative of the bottom, which is going to be 12x squared, times the top, which is 5, all over the denominator squared, so 4x cubed plus 4, all in parentheses and squared. Now you can notice that this all cancels out, and so I'm going to just simplify it a little bit, and then this becomes negative 60x squared all over 4x cubed plus 4 squared. Okay? That would be my derivative if I use the quotient rule. Okay? Nothing wrong with that. But I could rewrite this, and now I could have rewritten this guy and processed it a little bit differently. But I'm going to rewrite this so that it's a product. I'm going to make this all a negative exponent. So we'll say f of x equals 5 times 4x cubed plus 4 to the negative first power. Okay, to the negative first power. Now from here, I don't want to fall into a trap of trying to apply rules that we don't understand yet. This is actually going to be dealing with the chain rule. The chain rule, we'll get to that in the next, unit, I believe. But so I can't really do this right now in front of you, but I'm just showing you that you can rewrite an expression and find a derivative using a different rule here. Again, this would be the chain rule, and it will produce the same thing. We're not here yet, so we have to apply the quotient rule. And to be honest with you, I forgot that was going to need the chain rule. I thought I was going to be able to use the product rule or something there, and oh well. That's why I wrote it down. But anyways, let's go on to the next one. Number 3, g of x equals rad x over natural log of x. G of x equals rad x over natural log of x. All right. Well, rad x can be rewritten, and it's always a good idea to do this. This is x to the 1/2. Now, you'll get it in your brain. You'll eventually memorize that the derivative of rad x is 1 over 2 rad x, like this, 1 over 2 rad x. But just for now, because we're still practicing these rules, we'll do the derivative by rewriting it. And it's always a good idea to do it anyways, just to make sure you're right. So the derivative at the top is 1/2 x to the negative 1/2 times the bottom, so times natural log of x, minus the derivative of the bottom, the derivative of natural log of x is 1 over x, and then times the top, so times x to the 1/2, all over the bottom squared, so natural log of x squared. All right. So g prime of x then can be simplified a little bit if you want. It would be 1 over 2 rad x times natural log of x, and then this guy's actually going to be 1 over rad x, because we subtract those, we get x to the 1/2 on the bottom, all over natural log of x squared. The reason I put parentheses around this is because if I write natural log of x squared, this kind of implies that we're squaring the x. We're not squaring the x, we're squaring the whole function natural log of x. So that is my answer for g prime. Whether that can be simplified further or not is really beside the point, because we don't have to simplify anything unless we need to use it for something else. But that's pretty much what we have here, okay? And then number 4. Number 4 actually can be done using 2 different methods. We got 2 over 3x to the 4th, y equals 2 over 3x to the 4th. So quotient rule would say y prime equals 0 times 3x to the 4th minus 12x to the 3rd times 2 all over 3x to the 4th squared. And I will simplify this a little bit. This will end up being negative 24x to the 3rd over, that would be 9x to the 8th. And then we'll simplify that a little bit more. Common factor of of 3, so that's negative 8 over 3. And then the bottom will have x to the 5th there. So that's my derivative. If I wanted to, I could rewrite this so that the exponent's on top. So I could rewritten this as 2/3 x to the negative 4. I like this better because I can just use the power rule. So y prime equals negative 8 over 3 x to the negative 5th. And then rewrite that with a positive exponent, so negative 8 over 3x to the 5th. So you can see 2 different ways of doing it. Obviously, this one is way more efficient, but we're getting practice with quotient rules, so we want to be using that one. All right, and the last problem, number 5. Number 5 is a bit of a doozy. Okay, we have h of x equals 3x times sine of x all over x plus 1. Now, this is where I find students first starting off not recognizing something very important from the last lesson I talked about. Remember, I said the product rule is everywhere. We've got to be willing and able to identify when to use the product rule. Notice in this case, we have a quotient, and because we're learning the quotient rule today, we think, okay, all we're going to do is the quotient rule. But we also have a product, so we have to be careful with this. Now I'm going to do this off to the side. I'm going to say that let h of x equal u over v. If that's the case, remember the derivative would then be u prime times v minus v prime times u all over v squared, quotient rule. Okay? The problem is, comparing these two functions, what is u? U is the numerator. U is the numerator. So if I was to write that down, if u is the numerator, that's 3x times sine of x. And then v would obviously be the denominator, x plus 1. Okay? Now, if I need to determine the derivative, to do that, I've got to figure out the derivative of u. I've got to figure out the derivative of the numerator. I have to figure out the derivative of this. The derivative of this is not just 3 cosine of x. It's a product. We have to use the product rule. So I'm going to go ahead and write that down. The derivative of u, remember, product rule, the derivative of the first thing is 3, times the second thing, so times sine of x, plus the derivative of the second thing, which is cosine of x, times the first thing, 3x. And again, put parentheses around these functions because we don't want to try and put this x together with this 3x. You cannot combine those in any way. So we should probably rewrite it a little bit so it looks a little bit cleaner or a little bit more something we're used to. I'm going to put this 3x in front of the cosine of x. Okay? So this is the derivative of u prime, or sorry, the derivative of u. Now I've got v, which is x plus 1. I also need v prime. So, well, what's the derivative of v prime? It's just 1. The derivative of x is 1. The derivative of 1 is 0. And so now I have all the pieces that I need to plug in to find my derivative. So h prime of x, remember quotient rule. What's the derivative of the top thing? Well, this is the derivative of the top thing. So 3 times sine of x plus 3x times cosine of x. That's the derivative of the top. Times, notice I put this in, I should put that in brackets, times the bottom thing, so times x plus 1 minus the derivative of the bottom thing, which is just 1, times the top thing, which is 3x times sine of x. Okay? All over the bottom, the denominator, squared. So that is my derivative of that function. All right. That's gross. I am not going to simplify that any further other than you can just knock off that 1 there. Yeah, I'm not going to simplify that any further. I mean, I might be able to take out a 3, common factor of 3 out of everything, but we're going to leave it like that. Let's see if my answer agrees to make sure I am correct before we move on and assume everything's good. So you can see I've got my x plus 1. I just put that earlier. Times 3 sine of x plus 3x cosine of x, and then minus 3x sine of x without the 1, x plus 1 squared, and we leave it like that. All right, that wraps up this actually very short lesson. Like I said, it was going to be pretty quick. We're starting to roll with this stuff. We're starting to get all these rules down. We got the constant rule, the constant multiple rule, the sum and difference rule, with the power rule. We now have the product rule and the quotient rule. So we can start applying more and more of these rules to find derivatives, which means we're going to eventually get to a point where we can start using derivatives in everyday life and in a lot of different applications. So we don't have to sit here and practice calculus. We can start applying calculus, and that's where it gets really fun. So with that said, if you have any questions, please comment below. Otherwise, we'll talk to you later.